In our second installment of rates of change for multivariable functions, we're now going to take a look at some partial derivatives, which again looks like a foreign concept, but is actually quite in line with what we've been doing and exploring in these multivariable functions. So the question that we're going to look at first is find the partial of c with respect to d and the partial of c with respect to m and explain what each means. Okay, well, first of all, we know from our definition that this notation, the partial of c with respect to d, means that d is the variable or the input variable, and we are holding m constant. Okay, so when we held m constant earlier, for example, when we did the reduction function c of d comma 100, we would have found that the equation reduces to 1999d plus 47. Now this is exactly what we mean by holding m constant. In this case, we gave it a particular input value and we plugged that in, and we can see that what we have left is a univariate function. Univariate meaning we have one input variable. Okay, well that means that if we hold m constant, the rate of change of this equation here is precisely just the slope of the line, 1999. So we could write that in general, the partial of c with respect to d is equal to 1999. Okay, well, what are the units of this 1999? Well, notice that what this means is this is the change in c with respect to a tiny, tiny, tiny change in d, or an instantaneous rate of change. Well, regardless of how much you change d by, the rate of growth in the cost is going to be 1999. Well, it's over 1, which now if we look at the left and the right hand sides, we see that the numerator corresponds to the change in c and the denominator corresponds to the change in d by the structure of a slope, change in output over change in input. So this is 1999. I'll put the dollar sign over here just to keep our units to the right, even though we put the dollar sign in front. Per 1, well, that's the change in days. So what we would interpret this as meaning is that the change in cost per additional day at the instant of having, excuse me, not at the instant, doesn't really make sense, but driving 100 miles is going to be $19.99 per additional day. So if we increase the number of days by 1, we've got to increase our cost by $19.99. Okay, well, we generally don't want to have to plug in values for m. So when we take the derivative of c with respect to treating d as the variable, we just have to think in our minds that what we want to do is we want to take the partial derivative with respect to d. So really what I'm doing here is I'm just applying the derivative, saying I'm taking the derivative of this function with respect to d, which means I'm taking the derivative of this side with respect to d, because what we do on to one side, we've got to equally do to the other in order to preserve equality. And so I want to take the derivative of 1999d plus 47 cents m. Okay, well, this tells me what the variable is. Whoops. This tells me what the variable is. I'm looking at a change. I'm letting d be the variable. I am holding m constant. So anything that involves a letter, if we want to think about it that way, other than d is considered constant. So what I like to do is I like to put a box around anything that is going to be treated as a constant. So that's constant. And so if m is held constant, then 47m is constant. And similarly, this is a constant. So this is of the form 1999d plus some number, right? So 47m, if we're holding m constant, is just a number. Okay, well, what's the derivative of a constant? Well, the derivative of a constant is 0. And also, by the way, the derivative of a sum is we can find the slope of each individual term and add the slopes together. And the derivative of 1999d to the first power is, well, if you do the power rule, it's 1999 times 1 to the d, 1 minus 1, and that just turns out to be 1999. So we don't really even need to use the power rule there. We know that the slope of a constant, of a linear function is just going to be the slope of that constant function. So our answer is that the partial derivative of c with respect to d is 1999. Again, put it over 1, put the units of the c, which is dollars, put the units of the d, which is days, and this tells us that if we increase by this many days, we increase by that cost. Similar concept goes for the partial derivative of c with respect to m. Okay, now the partial of c with respect to m says m is the variable, or the input variable again, and we're saying hold d constant. Okay, so again, if you plugged in a number for d, you could probably see that 1999 times that number is a constant, but then plus 0.47 times the variable is going to form another linear function. So for instance, the reduction function c of 1 comma m is equal to 1999 times 1 plus 0.47 times m, which reduces to 0.47m plus 1999. And if I asked you what's the rate of change, well, you're going to tell me that the cost increases by 47 cents for each additional mile that I'm going to drive. In fact, it doesn't really even matter how many days you keep the truck for. You're always going to pay 47 cents for each additional mile that you drive. So if we looked at taking the partial derivative of the cost function with respect to treating m as the variable, letting d be the constant, well, that's going to be the partial derivative of the right side, which is 19.99d plus 0.47m. Okay, well, this is a constant, so I'm going to box that up. And this is a constant, so I'm going to box that up. Well, the derivative of a constant term is going to be 0. And the derivative of 0.47m to the first, well, that's again a power function. And well, what's the derivative of a linear function? Well, it's just the slope. Well, it's always just the slope, but the slope is always constant for a linear function. And so our output is 0.47. Okay, so partial of c with respect to m is 0.47. Again, I'm going to put it over 1, so I can show that it's a change of 0.47 to a change in 1. And what are the units? Well, my cost is going to increase by $0.47 for each additional, okay, what is m? M is the number of miles. So if you increase the number of miles by 1, you've got your cost is going to go up by $0.47 or 47 cents. Okay, so that's our first partial derivative. All right, well, let's do this for another function. Actually, before we do that, well, I guess we can do it here. So here, this is the compound interest formula, and I've done a reduction function on it already. And if you're familiar enough with the compound interest formula, then what I've done here is I'm looking at an investment where I'm going to invest $100 on a bank account compounded monthly, and I'm going to let R and T be my variable. So to keep the notation clean and condensed, I've written A of R and T. We're only going to consider functions that have two potential input variables. So here, oh, by the way, we've modified this equation so that I've called it capital R instead of little r, so that R is actually the percentage instead of the decimal equivalent rate. So if it's 10%, we can plug in 10 for R. And this 100 down here actually does the division and makes this a 0.1 for us. But it makes more sense because if we talk about the change in 1 unit of R, if R is a decimal, then that means you've increased your rate by 100% if you've increased little r by 1. But if you increase capital R by 1, that's just adding an extra percentage point to your interest rate. Okay, so find a sub r of 5, 10 and a sub t of 5, 10 and explain what this means to an investor. So note that using this notation, just as a reminder, this is the same thing as saying partial of a with respect to r. Okay, so let's do this one first. Now, before we plug in any numbers, we're going to, and this implies that we're taking a partial derivative. What we want to do is first take the derivative before we plug in any values. If we plug in values now, then this whole thing reduces to a constant, a single number, and then the derivative of a single number of a constant value is 0. Well, constant doesn't have any rate of change. Okay, so let's see what we're talking about here. We are saying that we are treating r as the variable. You know what, let's come back to this example. I realize this is going to require a little complexity that we're not ready to explore. Let's just go ahead and do some computational examples. We will come back to that. Okay, so a few examples here. We have the partial of this function with respect to x. And by the way, there are no other variables here. There are no other variables. So this is just a regular one single variable function, but we've just happened to use the partial notation. My point here is that you can use the partial notation and it doesn't mean anything new or different. It's just if you only have one variable, then you could really just say d dx. But in general, with multivariable functions, we often you see the partial sign more often than not. Okay, well, what's the derivative of 3x? Well, the derivative of 3x is 3 because that's a linear function. And the derivative of a constant is 0, so our partial is that this function has a rate of change of 3. And duly noted, because if you plot this function with the y-intercept of 2 and y is equal to 3x plus 2, it is a linear function and has a constant slope of 3. Okay, well now what about the partial of 3y plus 2, where x is the variable, everything else is held constant? Well, if everything else is held constant, that means y is not allowed to vary. Y is being held constant. So this is a constant term, a constant, and then another constant. Well, what's the derivative of a constant? It is 0. Okay, again, this is as if I had plugged in a number for y, for example, 10. Since y is not a variable, that means y is being held to a value, and a constant times a constant is a constant. So the derivative of a constant is 0. So this has no rate of change as x changes. It only has rate of change as y changes. Okay, well, let's make this a little bit more dynamic. Look at this function, and now it's the partial of 3 times x times y plus 2, and we want to figure out what's the rate of change in this function as x varies. Okay, well, wait a minute. So let's do a little bit of rearranging here. So this is going to be the partial with respect to x of 3y times x plus 2. Why did I write it that way? Because since y is being treated as the variable, we're thinking about, y is being treated as the constant, x is the variable, 3 times y is just a constant. And again, 2 is just a constant. So I have a number times x plus 2. This might as well be 15x plus 2. Well, what's the derivative of 15x plus 2? The derivative of 15x is 15. The derivative of 2 is 0. And down here, that number is not 15, but it's 3 times y. So in this case, the derivative would just end up being 3y. Let's do another one. Okay, partial of this with respect to x. So again, I'm going to do a little bit of rearranging here to cluster my constants together. X is the variable, y is being held fixed. So I have 3yx, push all my constants to the forefront. And also in this other term, even though this looks intimidating, y to the 100th. Well, if y is being held constant, then y to the 100th is still a constant, and 3 times a constant to a constant is still a constant. And so now I can see that this is really just a linear function in x, meaning that I have this is the coefficient in front of x, and this is the coefficient in front of x. And that's just like saying, what's the derivative of 6x plus 12x? Well, the derivative of 6x is 6, the derivative of 12x is 12, 6 plus 12 is 18. Here, the difference is that the derivative of constant x is the constant. The derivative of constant x is the constant, and there is my partial derivative. Well, let's look at the same problem, but now think about y as the variable. Okay, so that means x is a constant. Okay, well, I've already got this rearranged to where my constants are pushed to the front. And here I've got my constants pushed to the front. So I've got a constant times the variable plus a constant times the variable to the 100th power. This would be the same thing as differentiating 10y plus, 60y to the 100th. Well, the derivative of 10y is just 10. The derivative of 60y to the 100th is 60 times 100y to the 99th. And so, okay, well, it's the constant here is not 10 and it's not 60, it is 3x and 3x. So therefore, the derivative of constant times y is just the constant, which is 3x. And the derivative of constant y to the 100th is constant times 100y to the 99th. Okay, so the constant is 3x times 100 y to the 99th. And if I want to combine like terms, I suppose I can. 3x, 3 times 100 is 300, and I have 3x plus 300 y to the 99th power. Done. I've got a couple of partial derivatives under my belt. Okay, so let's go ahead and take a look at this example first before we go back to the compound interest problem. Consider the volume of a Coca-Cola can, which has a volume of 355 milliliters, which is 12 ounces. But since we're going to measure it in centimeters, when you multiply centimeters by centimeters by centimeters and get cubic centimeters, a cubic centimeter is the same thing as a milliliter. So it's appropriate to measure this in centimeters and milliliters. Okay, does it make sense to increase the radius by 1 centimeter or the height by 1 centimeter? So suppose you have the choice and you want to make the decision of which one is going to be more economical or is going to basically increase your in this case, volume by mole. So here's our Coke can, and we're going to assume for simplicity that it's a perfect cylinder, which it approximately is. And this is the height of the can, which is going to